Record the screen. Perfect. So I was saying there is something I wanted to cover, but I wasn't sure how many of you will need it, but it's important. So that's what I'm going to do today. I could have used the other stuff where I can write on the board and sketch, but I think that would take more time. So I went the harder way, which was to put everything on the slide. So this took much more time than I thought, but I think this is a better way. You can have it and then you have the slides. You can always refer to it. So I talked about G.cells, right? We looked at different things, but we didn't look at these two, G.cells.faces, and then G.cells.face position. We didn't look at this, and this is important. This is used in the calculation of the fluxes and so on. If you find yourself working on reservoir simulation and you're using some loops, you're trying to say calculate flux for all the neighbors of different unstructured grids. So cell 1 can have 5 neighbors, cell 2 can have 2 neighbors, and so on. If you can't have 2 neighbors, it needs to have at least 3 neighbors for a triangle. If you want to do this efficiently, so the simplest way to do it will be you have a list of all the cells that are neighbors of each cell. So you have a column going down, right? And then the length of the rows, the length of the rows, which is the number of columns, is varying, right? How do I do this in an easy way? Because nobody does it this way, that's why I don't have it. So what I can do is to good. So if you have your list of cells, these are your cells. I can make it bigger. Max it out. This is a common implementation flaw that beginners always make. So these are your cells, but they are unstructured. So cell 1 would have 5 neighbors, meaning its neighbors could be 2, 4, maybe cell 18, and cell 19. And then this one could have only 3 neighbors. It's triangular. It doesn't put random values. And then this one has so many neighbors. So if you continue to do this, what you will have will be some irregular matrix, right? It's not of a fixed dimension. So typically in MATLAB, you'll be using cells to do this. And then when you want to find the flux around each of these stuff, you will have a weird loop that will be going from 1 to the number of neighbors, but you don't know the number of neighbors. So you keep looping until you get to the end and it's all messed up. So typically, whenever you find yourself doing this, know that there's a better way. All of these irregular matrix, which can leave you storing zeros, right, to make it up into a matrix, should typically be stored as a vector. And then you use what is known as an indirection map. And that's what we're going to see. That's what G.cells.faces and G.cells face position basically does. In computer science, another way to do it is called hashing. So you use hash tables so that you can automatically know where the neighbors of a cell are. And then all of this information is stored in something like a vector instead of much larger matrices, and then looping through is pain. So that's what G.cells.faces does and G.cells.face positions, basically. And this is what it looks like. You could go ahead and run the same problem we've been looking at over and over again, right? These grid structure web that I shared, you run it, this is what you get, right? You remember this, we know how to number it if we're focusing on the faces, right? We start with this, phase 1, 2, 3, and so on. Small, right? So font is somewhere here. Good. G.cells.faces. This is what you're looking at. I can't make this one bigger. But we will create this. So the second column is not as important as the first column. Let's focus. Let's do it here. So this is the grid you get, right? After you run that code, 3 by 3. This is the numbering of the faces. The purple, we are focusing on first numbering the X faces, right? Those X faces. When we are done with the last X face, which is 12, then we'll go back and number the horizontal faces, 13, 14, 15, all the way, and there are 24 of them. So this is how we're going to store that kind of information. So regardless of whether the grid is unstructured or structured, this grid, this data structure will work. And you're not working with matrices, you're working with just a vector, right? Because technically the second stuff is not really particularly useful. Let's do what we always do, right? Good. Pointer options, laser pointer. So face IDs, that's the most important. That's what we care about. So I want to list the faces here. But these are faces that do what? That cover cells, right? Remember, faces cover cells. So G.cells.faces. There is a different data structure, which is G.faces that we are aware of, right? What's G.faces going to be? It's just going to go from 1 to the last face. It's literally 1, 2, 3, 4, 5, all the way to 24. That's what is in G.faces. That's a list of. So those numbers, 1 to 24, they are the IDs of the faces. The faces have identities. It's 1 through 24. So those 1 through 24 is what is going to show up here. But this is going to be longer because you're going to repeat the faces multiple times. So if you focus on cell 1, because this is G.cells, focus on cell 1, you see it has 4 faces. Those 4 faces are what you're going to have in the 1 through 4 here. So this first item will be what? I've shown you the ordering they use when it's 2D Cartesian. It will be 1. So let's fill it. So I have to get out of here again, but try to make it as big as it can be. How do you do that? And then take this out. You all can still see this, right? Okay, so what's the idea of the first face that bounds, that's part of the faces that bound cell 1? We will always start from the left and then go in this anti-clockwise direction. So what's phase 2? Huh? We're going to use this ordering scheme anti-clockwise. So 13, we are not going to skip them, then 2. And then what? 16. So you can see these are phase IDs. It's telling you that phase number 1 is what is part of the list of phases that cover cell 1. Phase number 13 is the next one. Then phase number 2, phase number 13, phase number 16. And then you come here. So you are basically going to cell number 2, right? Okay, so what's this going to be? 2. And then you see now that we already repeated phase number 2, right? Phase ID number 2. Why? Because it's at the interface between these two. So it bounds cell 1, also bounds cell 2. So that's why this stuff is usually longer than the face, than the number of faces. How do I know the total length of this for this Cartesian? Who can tell me what this total length will be? How many rows will be in these G.cells.faces? Do you see any pattern? All the cells in Cartesian grids have 4 faces, right? 36, how did you get that? And there are 9 cells, right? So 9 times 4. That's exactly right. That's what this is going to be. It's just a list of all the faces that bounds all the faces that bound all the cells. So we've had the first 4 for cell 1, the next 4 for cell 2. Give me all the 4s for all of the cells, and there are 9 cells. So 9 times 4 gets you 34. But if the grid is unstructured, it still works. The length is what I've represented with this formula. Is you're summing over all the cells, right? And what are you summing? The number of faces of cell I. So that's what this is. Number of faces of cell I. So that's what the length will be. And so if you go in there in the code and do, how do you get the total number, the length of G.cells.faces? How do you get the length in MATLAB? Size, right? But this will, or better still, num L. Num L is the better one. But you need to tell it, because size will give you the dimensions, the number of rows on the column. And then here you want to tell it, you want all the column, all the rows, only the first column. That's 36. If you didn't tell it you wanted only one column, then you'll be getting the total length of the stuff, which has 2 rows. So good. That's that. The other thing we always like to do is to just go in here and say max. Do max on this. What do you think that's going to get you? Yes. So it's looking at all the different face IDs and giving you the highest. And then you will see, okay, this is actually 24. You're wrong. It's the maximum ID of the face. Yeah. So that's what's going on, because you can take a glance at it again. It's 1, 2, 3, all the way to 24. So that gets you the maximum. The other thing I wanted to show you there was that the number of rows, you can see that's 36, right? And then if you wanted to see the G.faces, just for completeness, where is that? Here. And then .num 24. So it's just 1 through 24 for the faces. Just like cells. When you do G.cells.num and you get the total number of cells as 9, you know that the list of cells is 1 through 9. Good. What else? That's the only way to reference this. Do like this way. Face index. So you all already confirmed this is 36. But we don't write anything. Yeah, actually, this number is equal to 36. So 36 will replace this formula. And you already see it works for any unstructured grids. Face index. This is basically saying north, east, west, south, or whatever. In 2D, it's just north, east, west, south. In 3D, north, east, west, south, plus top and bottom, because the grids can have. Okay, so in 2D, this is the ordering. West is 1. East is 2. South is 3. The north is 4. That numbering is different from what was used here. Here we went this way, right? 1, 13, 2, 6, anti-clockwise. So you will see that this is not going to be 1 through 4 because of that reason. So phase 1, phase ID 1, which is phase 1. Is it west, east, or south? Whatever it is the number you put here. So which one is it? Is 1 is a west phase, right? Relative to that cell. If you look at 2, is what? 2 is 2, right? It's east. This is it. But if we were to go down here, the same cell, but you're looking at, sorry, the same phase, but you're looking at cell number 2. Is it still 2 in that case? Now it's west, so it's 1. Oh, I was typing east here. This is 2, and west is 1. And what's 13? South. And this one has to be 4. And that pattern basically repeats because we've used the same ordering. And where it gets useless is when the grids become unstructured. You're not going to be having west and east, right? So when the grid has 7 sides. So this second column is actually redundant. Not a big deal. So this is the most important one, and you already understand what's going on. How about G.cells.face position? Because this is faces. This is face position. What do you think that does? It tells you the position of the face. That's what the face position does. So the first one will always be 1. The first cell we start with 1. This 2 is the index where the first face of cell 2 will be. So this is the first cell. This is the first face in cell 2, right? So you always start from the left, from the west is 2. What number is this on? This number 5, right? Row 5. So that's what will be here. 5. But if you think about it, how did you get 5? It's just the number of faces that bound cell 1 plus 1. Because cell 1 starts from 1. So it's bounded by 4 faces, right? 4 plus 1 gets you to 5. That's where the first phase in cell 2 will begin. Okay, cell 2 now has 4 faces too. The starting point for cell 3 will be 4 plus the 5, and then that takes it to 9, and it keeps moving that way. Does that make sense? So if you go into the code and you look at G.cells.face positions, that's what you see. It's first 1, then 5, then 9, just telling you the indices where they start from. What do you think the length of the number of rows, the number of elements in that will be? Each row basically corresponds to each cell. Remember, cell 1, you told it where it starts. Cell 2, where it starts. The only thing you need to do is, when you are done, put the index of the next cell, like NC plus 1. So that's why the length is number of cells plus 1, NC plus 1. Otherwise, there will be no way to figure out how many faces the last cell has. So if you do diff on this, what do you think you're going to get? So you use the diff function on G.cells. I'm not going to type enter. What do you think you will get from this? G.cells.face position is 1, 5, 9, 13 through 37. Huh? How long will it be a vector or a scalar? Diff will always be a vector. Right? Diff gets you the differences between, so it will be a vector, right? And what will be in the vectors? Yes, which in this case is 4, 4, 4, 4, 4, 4, 4. Each face has 4 faces. Do you see that? So that's the power of this. So that if each cell has different number of faces, this is how you get exactly the number of faces for each cell. And that's how you create it if you were the one creating g.cells.face position. But you didn't create it, right? MRST did. So that's the algorithm. It basically will figure out each cell, how many neighbors does it have? Instead of storing it the way I showed you nobody does in Excel, then store the indices where each one will start. So if we were to do it for these so-called unstructured grid we didn't think about, the first cell will be 1, right? Then the next one will be what? 1 plus the number of neighbors it had, 4, so 5. And then the next one will be, this one had 3, right? So plus 3, 8. Then this one had how many? 6. So it becomes 14, and so on. And when you're done with the last one, 19, let's assume it was 45 or 43. You will need to add one more, which will be the number of faces cell 19 has plus this. So let's assume it has 3. Then there will be one more, which will be 46. And when you do diff, you know, when you use diff on something, that vector becomes 1 shorter. Does everyone know that diff function, whether in MATLAB or in Python? Both programming languages have that. And so that's how you use that. Perfect. Any questions so far? This is topic 4. So that's what I explained here. And go grab whatever the result you get from this, add it to the number of faces cell 2 has, add it to the number of faces cell 3 has, and so on. And when you are done, what will be the total length? So there are different things going on, so maybe I should take it slow. This one will be NC plus 1. We already talked about that. This one will be what? $37 for our problem. It's going to be the total number of, the number of faces each cell has, sum them all up, which was 36 from here, and then just add 1 to it, and that's what the length will be. But you will have gotten that by just following this algorithm. Perfect. So I've addressed everything here, right? What if this thing was 3D? What if it's 3D? What changes? Starting all the way from the left. Yeah, let's do it together. Duplicate, because your real problems are going to be 3D, and you need to be able to do, especially those of you saying you want to work on fractures. You will need this if you ever need to go into the fracture list. So if it's 3D, how do you number the faces? So that's why I said you start all the way from the left. You actually start all over again. Why? Even if it's the same problem, right? But we extrude it. So you now have top and bottom faces. So it's like one row in a Rubik cube. So they are, originally, we're just looking at a plane. Now it's like a 3-dimensional object, but only one cell in the Z direction. How do you do that in MATLAB or in MRST? That's what I have here. Right? Just add 1. So it's now 3D, but only one layer. And the length is also 1. So let me just run this so that when I start coming back here to look at it, that's fine. Saved it, right? Control S, editor, run. So we run it. If you want to convince yourself it's 3D, just rotate it. If you had rotated the other one, you're not going to see this. So this is what it looks like in 3D. So now, in addition to the north, east, west faces that you were looking at before, there's now top and bottom faces. Do you see that? So the number of faces will be more than before, right? Previously, the faces were edges, right? Edges cover faces. That's what you're seeing here now. So this is an edge. This is another edge. And then there are two interior edges. So those edges are now faces. And then the numbering scheme. How do you think we're going to number it now? Exactly how we numbered it before, but we are not done. So all of those, yeah, I don't know why I have to do this because I maxed it out, but I'm not going to change that. So this numbering so far, this loop does not apply, right? We said that loop is only for this 2D. In 3D, we're just going to go 1 through 6. So you will not have 1, 3, 2 in 3D. You're going to have 1 to 6. You're not going to be going clockwise. Because how do you go clockwise in 3D? You're just going to do west, east, right? When you exhaust west, east, then you go front, back. Front comes before back. Then you go top. No, bottom comes before top. And then you go to the next cell. You know you're going to have 6 faces, right? We will come to what this should be afterwards. So this will just be 1 to 6, 1 to 6, and so on. So again, it's redundant. Now, this numbering, like I said, remains the same as before. So no need to repeat this. There are some faces we have not numbered. Those are the faces we want to number here. So what are those faces we haven't numbered? Top and bottom. So wherever we stopped, that's 24, right? Then we continue and then we go to 25, right? So this will be 25, right? Where is 26? Here, the centroid, right? It's not really the centroid, it's the center of that face, right? I'm just putting it in there. And you will continue this and so on. I'm not going to number all of them in the interest of time, but I'll jump to this one. What number would this be? Huh? 28, exactly right. And all of these numberings, what are they for? Is it for the bottom face or the top face? Huh? Bottom face? This is where you find out. Or this. Which face are you going to take first? Bottom always comes before face, so this is for the bottom face. Bottom face. Forget about this for a second. This will repeat, right? What's this number going to be? The last cell here, the last face on the bottom, the last bottom face. Okay, 29, 30, 31, 32, 33. Exactly right. And then we go to the top, right? These are the top faces. So this will be what? 34. What will this be? Good. I think those are the ones I might be able to get to here. So now, face ID. The first face. So we'll be starting from here, right? Because you have to do left face, which is the west. Now, left face, right face. So left face is 1, right? What's right face? 2. So you come in here. This is 1. This will be 2. Does that make sense? Is there a quick way to clear all? Does anyone see clear? No. That's fine. We'll just be replacing it. So it's 2 and it's phase 2. This is actually giving you the key, right? Go find the third phase, which is the what? South. So what's the south phase? It's going to be here, right? 13. Does that make sense? The northeast, west, north, east, west, and what? Which one am I missing? South. Those 4 numbers will come from this grid on the previous slide. It's only the top and bottom faces that we'll need from here. Does that make sense? So this is going to be 13, right? That's the south face of index number 3. And then the next one, the north face, is what? 16. So we come back here, 16. And this is correct. 1, 2, 3. How about this? Exactly right. That bottom face first. And what's the next one? 34. You guys are, am I missing something? I've pasted something over something, right? 13, 16, 25, and then this one is 34. And then we'll go to cell 2. And what's its own left face? Exactly. And then 3, right? And this is 1. Am I screwing something up? Yes, I am. For sure. I'm supposed to be here. 34. I'm switching from one slide to the other because they look so much alike. This is the one that is 2, and then 3. Yes. So everyone can complete this table. How about completing it with MRST? G dots, just to convince yourself that what we're doing is still right. G dot cells dot faces. Can you see 1, 2, 13, 16, 25, 34, and then 2, 3? This is where we stopped. And you see we are identical to these results here. So if you want to write a function to create this, you know how to do that now because you know the pattern. Yes.
For 2D, you go anti-clockwise. So it is 1. If you go to face ID.
Yes, you're right. Here, right?
Yeah.
This is what you're referring to.
So the face ID is 1, 13 to 16.
Mm-hmm.
The face index is 1, 3 to 4. Oh, because okay, but we will still follow the same convention for face index. Okay.
Yeah. So in 2D, this is how it is. That was clear. When you go to 3D, you will go 1, 2, 3, 4, 5, 6, but you are not going to go anti-clockwise. No, you're going to go left, right, because there's no way to say anti-clockwise in 3D. Right? It's 3 dimensions. So we'll just go left, right, front, back, but bottom, top. The bottom will come before top. Perfect. Any questions? We can complete this table, this figure later, but I think that part is very clear. How about face position? Does it change? So you realize that this formula remains the same, right? Except that there will be more faces. Before we did 4 times. Okay, so how many faces are we going to have for this problem now that we've extruded to 3D? What's this number going to be? You don't need to tell me the final answer. You can tell me what the product is. So what's it in terms of this problem that we're looking at, the 3Ds with single line?
Yeah.
6 times 9, because each of the 9 cells have 6 faces. So that's correct. 9 times 6. That's what you get. So let's move to this. What happens here? You now know NF is just 6 now. Before it used to be 4. Number of faces is 6. So the first index will be 1. The next one will be what? What am I supposed to type here? Seven, correct. 1 plus 6. You're adding 1 to the number of faces. You can look at this. This is the shortcut for you. This is saying how many faces does cell 1 have? That's what NF1 is. So how many faces does cell 1 have? Number of faces in cell 1 is 6. 6 plus 1. So that number will be 7. The next one says, how many faces does cell 2 have? Plus whatever you got in the cell above, which is 7. So 7 plus 6, 13, and so on. And this is all powerful. Again, it works for unstructured grids because if you add 8 neighbors in 3D, you will just be adding the number of faces for each of the cells down this way. So that when you do diff, like we talked about before, what you'll be looking at will be the number of faces for that unstructured grid. It works in 2D, works in 3D. Perfect. Any questions? So this is the indirection map, particularly this guy. You're using this guy to index into this, and then you can find all the faces you want. So when you want to look for each cell, this one already tells you where you're going to start and stop, right? 1, 13, and so on. 1, 7, 13, it tells you where you start and stop, and the actual faces are sitting in G.cells.faces. The combination of those two vectors, more or less, if you ignore this, is basically 2 vectors. It gets you what you would have obtained in a very inefficient way doing this. And then the start and stop indices for your loops, you will just be getting it from G.cells.face position. That's the whole wisdom and efficiency you get using that approach. Where are we? Good. Any questions? Is that part very clear? Yes. What did I say?
What does the
Huh?
what does
The diff.
the combination of face ID and face?
The combination of G.cells.faces, which is basically the face IDs. We are ignoring this last stuff. We can actually delete it so it makes our conversation easier. Delete columns. The combination of this vector and this vector has all the information that is sitting in this weird, inefficient scheme. It's also more efficient because it's just vectors. No zeros are stored. If you want to loop in this, you'll be finding the length of each of these stuff, which is extra computation. If you use this approach, which we're talking about, 4. We use this approach, the way to do that same loop will be you just looping from 1 to whatever this value is. You see that? The first one will look from 1 to what this value is. Next one will look from what this value is. The length of that stuff is already, basically you're looking from 1 to the diff of this, because the diff will get you the length of all of this. So you just have a diff vector, you store all the number of faces, and then you'll be looking from 1 to the number of faces at that corresponding index. For cell 1, you'll know you're looking at the ith index, basically. When I is 2, it grabs the corresponding length you will look through. When I is 3, it gets the corresponding length you look through, and it's all changing. And then you're still working with just a lean vector. So that's the whole wisdom. And then for when you need those actual cells, you go grab them from g.cells.faces. You see that? So you are looking from 1 to a certain number, then the actual faces are here, and you'll be grabbing them here too. So that's the way. If you ever find yourself working with something that is changing in length, you can implement it this way in direction maps. And it's very efficient, it's fast, it's faster because you're not going to be calculating length of each one. And it's also going to store, it's going to use less memory. So speed and memory efficient. Good. Any other questions? I will upload this video right after the class, so you might want to watch it again and think through this approach and think about problems you're working on, or anytime you're going to be working on this kind of stuff. Just revisit this and try to use it. So we are moving on, one step further. What we saw was g.cells.faces and g.cells.face position. And you see how we can use both of them to loop and get whatever we want, because faces cover cells. Now we are moving on to nodes covering faces. We talked about this at the beginning, that technically nodes cover edges and then edges cover faces. But in reservoir simulation, conventional reservoir simulation, we never need the edges. We just ignore the edges, right? All those nodes that give you 4 edges basically cover a face. So we just say nodes cover faces and we move on. So g.faces.nodes is what you're looking at, and g.faces.node position. And you can already guess what is happening, right? We're doing the same kind of stuff, so that any number of nodes can cover a face. And then when we need to loop through all the nodes that cover a face, we'll use the same kind of indirection map. Now, we need to number things differently, right? Because you're working with nodes now. So now I've numbered the nodes. Again, 1 through 4 and so on. So we are numbering nodes, and nodes are vertices. I hope that's clear. Nodes are vertices, they are not centroids. So that's the list of nodes, is 1 through 16. So how do you think we're going to fill this up? You can see here, they don't even store that second column we said was redundant. So we just need the node IDs that will cover the first face, and then you move on to the node IDs that will cover the second face. You want us to continue in, let's continue in 2D first. Let's go back to 2D, because we haven't numbered all the nodes in 3D, right? In 3D, you will basically repeat this. All of this is for the bottom. And then you have another 16 nodes on top of this. Does everyone see that? That's all you will need to do to go 3D. But let's come back to 2D again. So we are back in 2D. We are looking at this. What do you think I have here? The first node, 5. Does everyone agree?
Isn't it not supposed to be 5, 1, 1, 2, 6, 5?
So now, you know, before we were working with cells, and we knew the ordering of the cells, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, Chico has figured out that here you're looking at faces. So your numbering of these faces is 1, 2, 3, 4. That's the one that got to 24. So you will start with all the X faces. That's what I like to call them, right? Phase 1, 5, phase 2, 6, phase 3, 7, phase 4, 8, then phase 5 now until you get to phase 12, 16, and then you come back down to phase 1, 2, phase 1, 2, 3, and so on. So that's the approach. So you need the nodes that bound the first phase. First phase is this, so it's 1, 5. Chico is exactly right. And then you go to phase 2. What nodes bound phase 2? Just double check that we are not just doing our thing, right? So we'll go run MRST again and go back to 2D, right? So this is the 2D stuff. And then comment it out. Then run this guy. And then go look at g.faces dot. I have all of them opened. So g.faces dot what? Dot nodes. It's correct, you see? So you want to always double check what you're doing. And once you see, oh, you match the first couple stuff, you already know you figured out the logic. So that's to prove to you we are not just doing our thing. We're actually right. So the next thing is 37, right? And so on. 3748. That's up here. What will be the length of this? Basically, what number is here? What's the number? Or you can tell me the product or whatever for this specific problem. Number of faces times 2. Exactly right. Is that correct? This is number of nodes that bound a face. Sum over here. It's already here, right? So you're right. Because each face has 2 nodes. So number of faces, total number of faces times 2. So obviously that's longer than g.faces.num. Why? Because we repeat faces. You haven't seen us repeat yet until we come down. I mean, we repeat nodes. When we come down to face 1, 2, or edge 1, 2, technically, you will see we are starting to use 1 and 2 again. And then we use 2 and 3 again. And that's why it's longer. So that's correct. So it's number of faces times 2, which is 24 times 2, right? 48. You can go double check that in MRST. It's 48. Good. I stumbled on how to switch quickly. Just swipe left and right. Good. How about this? Remember this, right? From g.faces. From g.cells.face position. Now we're looking at g.faces.node position. That's what completes the indirection map. It will always start from 1. And the next one will be the number of nodes that bound face 1 plus 1, right? So how many nodes bound face 1? 2. So this one will be 3. And then how many nodes bound face 2? 2 plus whatever was here, which is 3, becomes 5. So basically, you're just looking at odd numbers starting from 1 in 2D, right? What will this give you? Two. Basically, and the length will be number of faces plus 1, because you always have to account for that last one, so that when you do diff, it will now be number of faces. And then you're looking at 2 for all the number of faces in there. So you have 2 24 times, because there are 24 faces in 2D. No, this one will be 135 all the way to, no, it's 135, so it will get to 51, right? So you need 135 that ends with a length of 25. So that would be whatever. You want to see it in MRSD, you can. So we are not. G.face. Let me just look up. Oh, I think it's g.face.node position. I must have opened it already. This is it. So it's 13579. It will have a length of 25 to get you to 49. You're right. But when you do diff on this, you know the last one will be 49 minus 47, which is 2. And the first one will be 3 minus 1. And the fact that you're taking differences, the length will come 1 shorter, and that's 2 through 2. If you add 2 faces, if you add 3 nodes, Actually, it's not meaningful in 2D. It's in 3D that you will see that you can have arbitrary numbers. It doesn't have to be 2 all the way. Here, there will always be 2 because 2 nodes will need to always bound an edge. So this is trivial. But that data structure is not trivial, meaning you can't just assume you know it. Why? Because we're going to move on and do 3D like we did before. So we are here. So any questions on this before we go to 3D? So you see that the pattern here is g.faces.nodes and g.faces.node position is doing something similar to what g.cells.faces and g.cells.face position was doing. And then you can loop exactly the way I explained for faces bounding cells. Now it's nodes bounding faces. So there are no questions. Let's do 3D. So we'll copy this guy. We will not finish it. We'll just talk about it. And we'll talk about what is mostly going to be different. So we already have this from the previous slide, and then this will now become 17. And then this will be 18, and so on. I want to do this. So what's this number going to be? 21, correct. And so on. So what's going to be different here? I actually like this. Bottom, remember, that 1 through 6 will never change. Is left, right. This numbering will be for the what? Bottom or top? I want to type something here. Is it that top or bottom? What's it going to be?
Oh, this is top. This is top.
This is top. Whatever you had before is bottom because bottom comes before top. That's what I was trying to give you as a hint. Because we don't want to repeat this one, right? This is bottom. What we use for the 2D is basically bottom when you go to 3D. So now you're looking at top. So now what numbers am I going to have here? The nodes bounding the face. Huh? And that's it. After 1.5, what do you have?
21 and 7, no. Yeah, 21 and 7.
How many nodes bound the face? Exactly right. So you guys see what is going on? This is all geometry. So Arun, you haven't contributed yet. Tell us what these first 4 numbers will be. Why not 1, 5, 17, 21? Go, Arun is introducing something else now that you would like to go counterclockwise because it's a plane. Who wants to take a guess? I've not checked this in MRST. Who is on the side of Arun, or you would rather go with 1, 5, 17, 21?
You will give it to 19 to 21. Like 1, 5, 7, 1.
Moment of truth. I think it's going to be counterclockwise. And if I'm to guess, I will actually want to start from the left, Arun. Instead of starting from 1, 5, I'll actually want to start from 21. 21. Yes, whatever that's, you want us to go there and look at it. So this is it. So I will say 21, 5, 1, 17. That will be my best guess. But any of those will work, really. Anything counterclockwise would be nice. The reason we do counterclockwise, so does anyone know why we always do counterclockwise in 2D? Is to keep your areas positive. You know, we're going to calculate, there are formulas for calculating area for triangles or squares, basically using the what's it called? The coordinates of the nodes. So if you want it to be always positive, that's why all the codes you're going to see in the literature will typically just go anti-clockwise. That's what we always get to you. So wherever you start is not really important. Well, let's see what they do here. So we need to go to 3D, right? And then comment this out. And then run this. So what do we get? G dots. Is this it? No, what we're looking for is G dot faces dot node. Aaron was right. So that's what they did. They chose to start all the way from 1 again, and then just keep going counterclockwise. And again, wherever you start is not important. Just make sure you go counterclockwise whenever you're looking at a plane. In 3D, there's no concept of counterclockwise. So that's one part I wanted us to see. So it was 1, 5, 1, 5, 5, 21, and came back. Yeah, 21, 17. So what's the next one going to be? Oh, because I didn't change this number. And that's correct. And then what would the length be? What would this be? They tell me the product, or what do you think it should be? Number of nodes. Times 4 in this case, correct. Number of faces times 4. So our number of faces was 24. So that's correct. And then this will be what? The first thing is always 1. What's the next one going to be? The number of nodes that bound face 1, which is what? 4. So it's 1, 5, 9, and so on. Do you see how this can be different now when it's unstructured? Because there will be more edges per face. And then you can use the div on that, and you'll be able to group and get all you need. So this is something important that I wanted to talk about, and you can see it's kind of evolving, but very clean stuff and very useful concept. Useful for port network modeling. You guys have something like this, right? When you want to figure out all the number of connections to, yeah. Useful anytime you have that kind of data structure. Sometimes it's referred to as hashing, and then the computer does the numbering and stuff. The computer knows where all the indices in the unordered list is. You check out hashing, but that's a more complicated stuff. I know people have implemented this kind of stuff with hashing, but this is the one that is more easy to understand for non-computer scientists. Yeah.
Node position is 1. Second one is 4 plus 1.
Yes.
That's 5. And the third one is 5, 4 plus 5.
Yes. Which is 9, and then 13, and so on. And the last one will be 1 plus the number of faces. So that when you do diff on it, it will give you the number of faces. And it will be all false in this case. Good. Perfect. That's one thing I've wanted to talk about. And with this, I can take any questions because I see I have only 10 minutes to go.
Next class, we will discuss again on some of scale distributed CMOS model.
MSRSB.
So, yeah, that's like.
You're also interested in that? Okay.
That's like what we like to call like,
So for me to do that, you guys will have to review that part of the chapter 4. Have you done that already?
yes.
You tried reading it? Okay, how about you? Okay, so you all should review the MSRSB in topic 4. It's the state of the art today. So multi-scale finite volume struggles when you start to go to compositional and so on. So you really want to use MSRSB. So read that part and then let's talk about it. That way it makes more sense. Any other questions?